in which we are going to show you on behalf of CAD and CYI two case studies for the zero energy houses. My presentation deals with the case of a zero energy house taken from the houses from Cyprus. And the CYI is going to be a real case, a real building with the application of new technologies. So, in this presentation, I'm going to enter with a brief introduction about the significance of the zero energy houses, and then I'm going to show the actual case study and present the conclusions that are extracted. We don't attribute importance to the energy consumption in the buildings because we are architects, because it's accepted, well accepted, that globally the buildings are responsible for 40% of the global energy use and 1/3 of the global greenhouse gas emissions. This is so for the developed as well as the developing countries. So these figures demand urgently the reduction of the energy consumption in the buildings. This is why the European Union has set very ambitious goals, the so-called 2020 goals. In these targets, it's anticipated that we are going to have a reduction in greenhouse gas emissions by 20% compared with those of the levels of 1990, and also raise the share of the energy consumption which is utilized by the renewable energy sources by 20%, as well as the improvement of the energy efficiency towards nearly zero energy buildings by 20%. In fact, it is expected that by 2050, all the existing buildings should be net zero energy buildings. Why do we consider the existing buildings? This is so because in Europe, only for the new construction, the annual rate is only 1%. And therefore, this makes the improvement of energy performance of the old building stock very significant. And this is why the European community attributes so much importance and high priority the refurbishment of existing buildings. And why the residential buildings in this presentation? Because the household sector constitutes 75% of the existing building stock in Europe. In the building sector, energy consumption is about 63% of the whole building sector energy consumption. And only 5% of the buildings are going to be, are expected to be from 2015 up to 2020. Therefore, the retrofitting of the residential buildings provides a significant potential for energy savings and the sustainability of buildings in Europe. And they also expect that when we do radical upgrading of the existing buildings, that is nearly zero energy buildings, then this will conclude to savings which are about 32% yearly of total primary energy use, And this corresponds to about 4 billion barrels of imported oil. What is a nearly zero energy building? A nearly zero energy building must have a very high energy performance envelope, energy efficient lighting, heating and cooling systems, and utilize the renewable energy sources. In this case study, which focuses on the conversion of an existing single family house in Cyprus, I am going to present one of the main residential typologies in Cyprus, which in fact constitutes 50% of the residential building stock, and how we reach a cost-effective, nearly zero energy building. So the objectives of this study is to fill in the current knowledge gap for nearly zero energy buildings in Cyprus, to assess and upgrade the energy performance of the building stock, and to highlight the potential of the utilization of renewable energy sources in the houses. What is the background of this study? This study has been performed within the framework of a European program, an IE, Intelligent Energy Europe project, European project, in which aims at energy efficient refurbishment towards nearly zero energy buildings in order to upgrade the performance of the existing household in the whole of Europe, in 17 countries in fact, and also establish efficient ways of monitoring the refurbishment of the household. So, in this project, primarily, we classified the households into different typologies, and according to certain criteria and to chronological periods, which we have defined. And we are taking one particular typology of this, though it concluded to three main typologies for Cyprus: the single-family houses, the terrace houses, and the multi-family houses. We are taking the single-family houses, and we are taking the one for the prior 1980, which is an existing, of course, building. So, the methodology that we followed for these case studies is that initially we made the selection of the house. We found the energy performance of this house and the existing state in terms of energy consumption and the construction characteristics, etc. We carried out simulations based on the directive which the government said, the Ministry of Energy, about the refurbishment of nearly zero energy buildings, and then we tested all the measures that we employed to see the thermal performance of each one and the cost effectiveness of each measure. So, from these simulations and the assessment of the measures, we developed another scenario, which we called optimized nearly zero energy building scenario. And then we are going to compare the two scenarios and present the conclusions from this. So, this is the building, this is the case study. It's a single-family house, as we said. It's a representative of its typology for the period prior to 1980. It is situated in Nicosia, which is the capital of Cyprus, and is inland. It's a single-story building with a heated area of about 135 square meters. It has an orientation of northeast to southwest. 15% of the total wall surface corresponds to glacis, and most of it is placed on the northeast and southwest orientations. It is considered to be an average building, really. It has 3 bedrooms and 3 bathrooms, an open plan kitchen and dining and living room. So, the characteristics of this building and which affect the energy consumption is that it has a non-insulated flat concrete roof. It has rendered brick walls, floor concrete slab in contact with the ground, double glazed windows, which have been refurbished in 2004. And the electromechanical equipment consists of 5 standard air conditioning split units for heating and cooling. And for domestic hot water, we have solar thermal panels on the roof, which is the normal case for Cyprus, since about 95% of the buildings have these solar thermal panels and backup electric system. So, the results of the simulation for the existing estate is that the energy consumption of the house reaches around 172 kilowatt hours per square meter annually. Most of the energy consumption is needed for the cooling, which is around 126 kilowatt hours per square meter annually, and 21 kilowatt hours for heating. And the rest are for the domestic hot water and the lighting. So that was the existing state. And we carried out simulations. And in this scenario, it's based, as we said, in the existing directive for nearly zero energy buildings, and it consists of, in order to fulfill these requirements, of 9 centimeters of thermal insulation externally on the roof, 8 centimeters externally on the walls, replacement of the windows with the thermally improved ones, that is with lower U value. This is a requirement also of this directive. Horizontal overhang shades above the south-facing windows, and 3 panels of photovoltaics, which have an area of about 5 square meters on the roof, which have an inclination of 30 degrees. And we substituted the existing air conditioning units with ones with A++++. So, the results of this scenario, which we call standard nZEB scenario, and is, as we said, the present requirements of the energy of the Ministry of Energy, is that the house was raised by 5 categories from Class F to Class A. The total final energy consumption is reduced to only 29 kilowatt hours per square meter annually, and the energy consumption for heating and cooling, lighting, domestic hot water, and I guess they became minimal. What we did now, we took all these measures that we employ for this standard scenario, and we examined them individually. We examined their effectiveness their energy performance as well as their cost effectiveness. So we found out that the placement of thermal insulation on the roof is the most effective measure, that the cooling savings that are resulting from insulating the roof are 3 times higher than the ones incurring from the placement of insulation on the walls, and that the replacement of the existing double glazed windows with new ones with lower U values, as it is demanded by this directive, results to minimal energy savings. And the placement of the 1 meter length overhangs above the south-facing windows is very energy efficient, only for cooling, of course. And about their cost effectiveness, we found that the most cost-effective measure, again, is the insulation on the roof, of course, with a payback period of less than 2 years. The horizontal overhangs have a 3 years payback time, and the insulation of the walls, 7 years. Now, the replacement of the double glazed windows with lower U value ones is the least effective measure, since it takes more than 1 century to amortize the initial investment cost. So, based on these results, we developed another scenario, which we call optimized scenario, in which scenario we did not do any window replacement, and we increased the number of PV panels from 3 to 12. That is from 5 square meters to 20 square meters. And we employed all the other refurbishment measures we did for the standard scenario. That is, we placed insulation on the roof and the walls. We achieved achieving the same U values as the standard scenario. We installed horizontal overhangs on the south-facing windows. We substituted the split units with ones of higher energy efficiency, that is A+++, and we placed the 12 PV panels, as we said. The results show that, again, we have a rising of the from F category to A category. The total energy consumption is reduced to the same levels as the standard scenario, around 30 kilowatt hours. The energy consumption of heating and for cooling are again, and lighting are again minimal, and domestic hot water. But we have the great difference here of the energy produced by the PV panels, which now rises to 34 kilowatt hours per square meter annually. So if we compare the two scenarios, the standard nZEB scenario and the optimized nZEB scenario, we see that we have the same levels of energy consumption, but with surplus energy production from the PV systems after the optimized nZEB refurbishment, and no CO2 emissions. The payback period for the optimized scenario is 7 years, which is 1 year less than the standard nZEB scenario. But bear in mind that there is going to be every year a surplus production of energy from the PV systems. So the conclusions we draw from this research is that the drawbacks of the minimum requirements towards zero energy houses, which are extracted by the Cyprus government, especially for the replacement of the windows, which is obligatory, needs revising. The replacement of the already double glazed windows, as we saw, has a share of 24% of the total investment, and it has a saving only of 2 kilowatt-hours per year, and it takes over 100 years as a payback period. On the contrary, the placement of shading devices is proven to be an energy effective and economical viable choice. So the bottom line is that the cost effectiveness of the different refurbishment measures on the building envelope, plus the high amount of energy produced from the PV systems, redirect the definition of the nearly zero energy buildings in Cyprus into more flexible and cost-effective choice in order to constitute a feasible choice of refurbishment for old houses. And each case must be judged and considered in its own merit. Thank you very much for your attendance. Now I'm going to pass the screen to Marina from the Cyprus Institute.
Hello, I am Marina from Cyprus Institute, and we will present with Alarik the new technologies laboratory building of the Cyprus Institute. During these presentations, we will see the objectives of the presentation, the infrastructure relevant to smart chains, the infrastructure of the building, and the laboratories and research facilities relevant to smart chains, the results of a recent energy audit, the novel technologies laboratory, the instrumentation, standards, U-values and ventilation, lighting, heating and cooling needs. We will see the solar thermal power system, the Fresnel collectors, and we will reach some conclusions. The main focus of the Nearly Zero Energy Case Studies webinar to be presented by Cyprus Institute, as we said, this pillar says the Nearly Zero Energy Construction Building, which is called Novel Technologies Laboratory Building. This particular building was selected to be examined and presented as it is a state-of-the-art infrastructure and among the very few available in the wider area of the Eastern Mediterranean. The building hosts laboratories, administration spaces, and seminar rooms of the Energy, Environment and Water Research Center, and is located at the outskirts of Nicosia, the capital of Cyprus. It has a total floor space of 2,130 square meters and consists of a basement, ground floor, first and second floor. The building is designed to meet near zero energy consumption criteria using advanced energy conservation measures, smart energy management, and solar, thermal, and photovoltaic systems to cover the remaining energy load. The energy conservation techniques which are used result in reduced energy consumption of the building by almost 70% compared with the conventional building, while almost 27% of the remaining heating, cooling, and lighting load is covered by photovoltaics. A concentrating solar thermal system for cooling and heating is being installed to cover the remainder of the load. Here we can see the building, and the main orientation of the building is south, which is completely unshaded. As you can see here, the elevation that is shown on both pictures is the south elevation. The building has no opening in the south-facing wall that we see, while the western and eastern facades are protected by an external metal cover. The main objectives of the design were the usage of sustainable energy sources, the reduction of the concentration of the emitted pollutants, the provision of thermal and visual comfort while staying indoors, improvement of the outdoor microclimate, provision of the best possible indoor air quality, usage of renewable energy sources and of intelligent metering and control systems in the building, and usage of environmentally friendly materials for the construction and maintenance of the spaces in order to avoid pollution. And now I will give the floor to Alarik
Hi everyone. Hello again. This slide shows the laboratories and research facilities relevant to SmartGen. The laboratories and research facilities relevant to SmartGen here in our case are two systems. First, measuring and control equipment, BEMS, and also we have the possibility to check online, let's say the real-time consumption and also the previous consumption during since the beginning of recording. So it means more than 1 year ago of all, let's say, the big components of the institute, of the laboratory. So we can, for instance, have a look on the PV which has been produced during 1 year, as you see on the top left, and on the top right, the consumption of the heat pumps. So you see heat pumps and chillers. So you see it's mainly concentrated in summer and also in winter. Also the lights, consumption of the lights, and which is mainly in winter, and consumption of the offices. So you can see on the right a service we contracted, which is Ether from Greece, and we can have a direct interface with the energy consumption of the building. So this building, as Marina said, it's not soft-oriented. So as you can see on the satellite view, you see that the north is pointing to the top, and the building is aligned with the north-south axis. At the east and the west side of the building, there is a perforated galvanized sheet iron, which has been installed with 60% of perforation. So this filter allows the direct radiation of the sun. So even on the west and the east. This way, between the grid and the walls of the institute of the laboratory, this creates a natural chimney and natural convection. So all the heat is released to the top of the building, creating natural convection and ventilation. There are very few windows facing south. So even from the start, it was already designed to reduce the energy consumption for HVAC. So here is the list of all the equipment which are at the institute for HVAC, so chillers, heat pumps, air handling units, and fine cold units, and also all the buffer time circulators and heat recovery units. So this is what has been inspected through an energy audit, which occurred last year in September. So all these equipments were audited in order to give a report, to give orientation to the Cyprus Institute for improvement, for instance. So here is a picture of all the equipment we have: one heat pump, two chillers, the fine cold units, air handling units, the PV on the roof, which is producing electricity, some stratified tanks, and the circulators. All this equipment is controlled by our BMS control, and it's a smart control which permits us also to reduce energy consumption. So the instruments that have been used during the energy audit are the following one. So as you can see, that 5 of them were used, and they were used mainly to measure the light, also the thermal losses, and the energy consumption, the U values, and for instance also the ventilation. I will not go into the details, but as you see, 4 floors were inspected, and you can see also the volume of each one. These are the standards which have been applied for the energy audit, so mainly for ventilation, indoor air quality, thermal environment, lighting, acoustics, energy efficiency, and thermal comfort. So these were the standards applied last year for the energy audit. So the energy audit showed that we had 4 main kind of walls, and the U value for each wall was between 0.25 to 0.3. watt per square meter per Kelvin. So in this case, as we see, the walls were, as we said from the beginning, they were designed in a way to reduce the energy consumption of the building. Some ventilation measurements for heat recovery, exhaust fan, air and air units have been identified as well, and you can see the class that each item, for instance, for exhaust fan at the Novel Technology laboratory, to which class each equipment is belonging. So you see we have between SFP1 to SFP4. And you can see also a picture which has been performed like around 8 o'clock in September, late September last year, and we identified some hotspots where we have some thermal losses. Lighting has been inspected as well, and the audit showed that mainly there were not really many improvements to be performed in our case, not like for the insulation. Now, if we look at the thermal needs of the building, as you can see, this is the plot for 1 year. So heating in winter and cooling in summer. So the cooling is provided by 2 chillers and 1 heat pump, and the heating only by the heat pump. So as you can see, there are high needs in summer and winter, and let's say that the intermediate season is really short. Also, as it is an industrial, or let's say it's a professional building, you can see that the hours of use are mainly based on office work, hours work, and no construction during the weekend. So this is very specific to our building. To improve, let's say, the drawbacks which have been identified from the energy audit, Fresnel collector has been installed on the roof on a building which is close to our building, the Novel Technology Laboratory, in order to reduce the energy consumption for HVAC, mainly cooling in summer. So this is a drawing schematic of our already existing HVAC system, which is in white background, and what we are now implementing with a gray background. So this relies mainly on the thermal storage, which is able to store the heat produced by the Fresnel collector at least for 2 hours. So this permits us also to ensure continuity of working and to provide cooling also to the building. So our linear Fresnel collector was installed on the Kepa school, which is on the roof of a building which is just in front of the NTL building. A linear Fresnel collector for non-specialists is composed by almost flat mirrors, 18 rows, 32 meters long. There is a low area density around 25 kilograms per meter square, so it's easy to integrate on buildings. This kind of collector has also a low wind load, so that's why we can fix it on the roof. In our case, we have 8 collectors in series, which are in between each beams, triangle beams that you can see, holding the receiver. It's not south-oriented as well, this collector. We use thermal oil that will heat up to 180 degrees. The power of the system is 75 thermal kilowatts. The end of the installation was in 2015, the mechanical installation. And this is the first kind of its kind in Cyprus and maybe also in many countries around Cyprus. This heat will be used afterwards to cool the building with an oxygen chiller, which is using heat to produce cool. The energy audit raised some improvement to be done. By now, our NTL, the use of electricity relies mainly on the heat pump consumption and the chillers. 71%, and 20% for the lights and 9% for the office for the offices. So as we can see, if we compare that to the production of the PV panels we already have on our building, it's just compensating only 20% of what we consume. So that's why we installed a Fresnel collector to reverse this balance, and we will be able to compensate almost at least 80% of the energy which is consumed by the NTL. It has been raised also, as I mentioned, that the lighting is already efficient, and the Fresnel collector is quite innovative as well, even though Fresnel is already innovative when integrated in on a building, but it will be also hybrid and produce electricity with photovoltaic panels, and this will reduce in a huge way the consumption of the heat pumps by the use of the oxygen chiller, and also by the production of electricity, which will complete also the electricity needs from our building. So as a conclusion, the preliminary design of the NTL permitted to reduce avoidable energy consumption by end user. So orienting to the south, no windows on the south, grids and PV panels. The energy audit identified the points to be improved, like insulation and the use of renewable energies. Cooling and heating are responsible of great parts of the electricity consumption in Cyprus. And this is not only for our building, but it's general from our country and the country surroundings. Using Fresnel collector will permit to reduce the electricity consumption and using less heat pump. And in a way also, by the production of a PV with a Fresnel collector, it will permit us, for instance, for the building to be autonomous maybe for 1-2 hours in case of our power outage from the mains of our electricity authority. Now, I will show you a small video of of the construction of the Fresnel collector. So these are the mirrors which have been installed. So you can see the lifting of all the equipment to the roof, installation of the supports, installation of the supports of the receiver, the secondary reflector of the receiver, the receiver is 32 meters long. Installation of the piping and insulation, which will contain hot oil, and now installation of the mirrors and tracking system. So this was built under nZEB project, also a European finance a project which has been financed by ELPI, and this Fresnel collector will be operative early next year. Thank you for your attention, and I leave the talk now to the Despina.
Hello again. I think we will open the floor to any questions and discussion. We have about 10 to 15 minutes. And we will be happy to answer any questions.
Hello, everyone. I am Denia.
Hi, Denia.
Hello. I have one question for the linear Fresnel. What is the status of the roof that was installed?
Hi. The Fresnel collector is more or less 11 meters wide and 30 meters long, so around 330 square meters.
And it covers how much energy of the building?
It's still not in operation. It will be maybe in January, but according to our simulations, it can be between 40% to 60%.
Okay. Very interesting. Thank you.
You're welcome. Thank you.
Any other questions? Well, although it has been presented in a very short time, it's a remarkable building actually in reality as well. It seems that Marina and Alaric have presented in a very clarifying way. So, are there any other questions?
I can have a comment. I think that it's good after a while to have some information during the course of the Smart Gems project, how this is operating and how these percentages that you mentioned and the real operation of the Fresnel collector, because it's very interesting to have this kind of knowledge for the Mediterranean buildings.
Yeah, okay. Thank you for your comment. I think it can be also a scope of a webinar one time, maybe next year, just to be operative a while and to give you main outputs. By the way, I can recommend you by now to go on STS-MED project website, and we already disseminate some things, and we'll also procure some let's say online lessons or online lectures as well with on-site let's say video. So in the meantime, this will be available, I guess, in the next months. So we can share this link to our partners, and you will have more details regarding our platform. And of course, we will share with you. Thank you for your comment, and we are really happy for your interest in that.
Thank you.
The comments by Alaric, which are very suggesting and promising, reminded me that to note that besides these single family houses, nearly zero energy, which I presented, you are going to find more information about the other typologies and for Cyprus and for the other countries on the EPISCOPE program, the EU program, i.e. EPISCOPE is written as EPISCOPE.eu. And you are going to find it on the website, on its website.
Okay, thank you very much.
If there are no other questions, would you like, Dania, to close this webinar for today?
Okay, I would like to thank you. There was very interesting presentations and very interesting results. Thank you all for being here, and have a nice afternoon. And when is the next webinar?
It's 16th of December, which is a Wednesday again. and we will send a doodle again for the time.
Okay,
But I
good.
think this time is good. It suits everybody. But in any case, we will send a doodle.
All right. Thank you very much.
Thank you, everybody, and have a nice afternoon. Bye for now. Bye.
Bye.
Bye. Bye. Thank you.
Bye.